Hey everyone, this video lesson is going to cover the atomic theory and how the atom has come to look the way it is as it looks today. Early observers of the natural world knew that the world around them was made up of 4 different substances: earth, wind, water, and fire. But it wasn't until the Greeks, who were the first to attempt to explain why chemical changes occur, and came up with the idea known as the atom. The word atom means indivisible. So, in other words, if you look at a handful of substance, eventually you'll get, if you split it apart and split it apart and split it apart and split it apart, you'll get to a smallest particle where you can't split it apart anymore, and they called that the atom. Now, for 2,000 years, alchemy, or basically the ancient art of trying to make things gold that aren't gold. And in the process, several elements were accidentally discovered. And other substances were created in order to separate or make these new substances, such as aqua regia, which is a very strong acid, and in fact it's a mixture of acids, including nitric acid and others. But alchemy, although really foolish, because as we know now we can't just make gold out of nothing, alchemy did help advance science and advance chemistry by discovering some of the elements that we know about today. Now, in the 1300s to 1600s, known as the Renaissance, and also into the Enlightenment in the early 1700s, we saw the birth of science as we know it. We began to start questioning everything we see and trying to relate these things to mathematical relationships and also create models and think more critically about the chemistry around us. I'd like to take a moment to talk about a couple of books that I've read over the recent years because I love science, and these are scientific history sorts of things. The first one I want to talk about is called The Measure of All Things. It takes place during the French Revolution in the late 1700s, where France got rid of its monarchy. The common people revolted against the monarchy and killed them, but that's only a side story. But as a result, they implemented a new government, and the new government was supposed to represent all people, even the regular person, from the poorest person up to the richest person. And so they wanted to implement a new system of weights and measures, also known as the metric system. In order to identify or to define the metric system, they needed to define the meter, because most things are defined by length. Cubic measurements, such as volume, are defined by cubic centimeters or cubic meters. And so if you know what a meter is, then you can start to talk about what a milliliter or a liter is. So anyway, they decided they were going to measure the Earth, because the Earth has never changed, according to them. And if you can measure the Earth precisely from pole to pole, divide it by a very large amount, you will get the length of a meter. And so they used astronomy and precise instrumentation to measure the length of the Earth from pole to pole, and then divided it to define the meter. What they didn't realize is that the Earth is not a perfect sphere. In fact, it's wider at the equator than it is at the poles, and so it's more oblong shaped or oval shaped, not perfectly spherical. But they figured that out during this process. Anyway, it was a very interesting read. It was really one of my favorite books I've read in the last couple years. The next one that I read actually further back was called The Age of Wonder by Richard Holmes, and it highlighted a number of scientists in the late 1700s and early 1800s, and specifically Sir Humphrey Davy. Daniel Faraday also gets a lot of coverage in this book because he was a protege of Humphrey Davy. But a lot of this conversation revolves around gases, and Humphrey Davy specifically used experiments with gases. He used some of his other influence and power to discover some other elements. Specifically, he was able to extract the alkali and alkaline earth metals from the earth using electrolysis by running electricity. He also did experiments with electricity in creating batteries. Another scientist that gets a lot of coverage in this book is Caroline Herschel, who was the younger sister of William Herschel, who was an astronomer who was hired by the King of England. He was the royal astronomer, but he worked closely with his sister, and she is credited with discovering a number of different astronomical objects, including stars, galaxies, and things of the sort. She was the first woman to receive a science salary from England, and she was also the first woman in England to hold a government position. She lived until her 96th birthday, and the King of Prussia presented her with a gold medal for science on her 96th birthday, which was pretty awesome. She is one of the scientists that was not often talked about in history. So in the 1800s, we began defining the fundamental laws of chemistry. And the two that we'll talk about first are the law of conservation of mass, which says that mass can never be created nor destroyed. In a chemical reaction, the mass that goes into a reaction is the same mass you get out in the products. The other law is the law of definite proportions. And it states that a compound always contains the same proportion of elements by mass. So if you know the mass of the elements in a compound, no matter how much you have, the proportions of the masses of the elements that make up that compound are always the same. So if you have 100 grams of water, for example, then of that 100 grams, a certain proportion is going to be hydrogen and a certain proportion is going to be oxygen. And that proportion is the same no matter if you have 100 grams or 200 grams or 1,000 grams. It's a definite proportion, explaining how compounds always contain the same proportion of elements by mass. So those two laws that we talked about on the previous slide gave rise to the first atomic theory hypothesized in 1808. Now, of these statements from the first atomic theory, some of them are still true today, and some of them have been since proven false. But these statements were accepted as true in the scientific community at the time due to the limited technology available to them. The first one says that elements are made up of tiny particles called atoms. This dates back all the way to the Greeks. So this particular statement of the atomic theory has been true since 2,000 years before. And the next one says that atoms of a given element are identical. The atoms of different elements are different in some fundamental way. Now this has since been proven false because elements, although have the same atomic number, may not be identical in mass because of the things that we know as isotopes. Says that chemical compounds are formed when atoms of different elements combine with each other. A given compound always contains the same relative number and types of atoms. Now this is a summary of the law of definite proportions, which we looked at on the last slide. And this is still true today. The next statement says that chemical reactions involve reorganizing of atoms and change in the way that they are bound together. That is true. We create and break bonds and form new substances in a chemical reaction. Finally, atoms themselves are not changed in a chemical reaction. In other words, atoms cannot be created or destroyed or changed in any way in a chemical reaction. And this is a gray area in science, and I would say that this is actually no longer true. Because of nuclear reactors and nuclear chemistry, we now know that you can take a substance and break it into smaller atoms if you can break apart the nucleus. And we'll talk about nuclear decay a little bit further on in this curriculum. But as of right now, atoms do change in a chemical reaction through nuclear decay. And that energy of decaying nuclei can be harnessed to power entire countries, or can also be used to destroy entire cities. So now that we've defined what an atom is, let's talk about some of the early experiments that kind of isolated different parts of the atom, the ones that we know today, the proton, the neutron, the electron. If you ask anybody off the street, so to speak, which particle of the atom was discovered first, many would probably say the proton, but in fact it was the electron, and the experiments with the cathode ray tube which helped identify the electron as part of the atom. Now, you take a tube and run electricity through it, and it lights up, as you can see down here, a stream, and that represents the particles that are emitting light. And so scientists said, well, we've coated this screen with some atoms, and when we run electricity from one end to the other, there's a beam of light that shows up. Now that light must come from a particle that's part of that coated substance, that coated screen inside the tube. And so there must be a part of that atom that is stimulated that will give off light. Now, they didn't know if it was positive or negative or whatever. They didn't really even know or define positive or negative, but then they started doing experiments. They subjected the beam of light to a magnetic field and noticed that it bent in towards the positive or the north pole of a magnet and bent away when they turned the magnet around. And so they identified these particles that produce this light as negatively charged particles, which we now call electrons. So the cathode ray tube experiment identified or helped us understand that there are negative parts of the atom, but how negatively charged, or what's the magnitude of the charge? And it was an experiment in 1909 that was performed on charged oil drops. And as they did these experiments, they were able to identify the magnitude, or how negatively charged a single electron would be. It also was used then to calculate the mass of an electron, a very, very small amount of mass, but a mass nonetheless. It was the experiment in 1911 that really brought the atom as we know it into view. It identified the nuclear atom. It identified an atom that has a very dense center with lots of empty space between the nucleus and the electrons that zip around it. I'll show you an example of what the experiment looked like on the next slide. But the resulting atom that came out of this experiment was different than the one from before. The results of the cathode ray tube experiment showed an atom that had negative charges embedded into a positively charged matrix. The atom itself was positively charged and the negative charges were embedded into it. Imagine chocolate chip cookie dough, where the chocolate chips are negatively charged electrons and the dough itself is positively charged. Not a lot of empty space in this version of the atom. The gold foil experiment took the negative charges away from the nucleus, leaving lots of empty space between the nucleus, the green in the middle, and the electrons, which are occupying space around the outside. Here's a basic representation of the experiment performed in 1911. They put a radioactive substance inside a box, and they poked a hole in the box so that only one spot where the alpha particles that were the result of a radioactive decay could escape, and only in one direction. So they zoomed out of this box and they went towards a piece of gold foil. Now gold was used because it is a substance that can be pounded very thin, only a handful of atoms thick, and then suspended in air, and then the particles were able to pass right through it. Most of the particles, as you can see, go through with no scattering, but the fact that some of them scattered at a slight angle and others at another more severe angle means that there must have been something in the middle of the gold atom that caused the particles to repel. And the fact that they use alpha particles, which by nature are positively charged, if the particles hit there and stuck and didn't go through, then they would say, oh, well, it's negatively charged and they must be attracted. But they went through and were deflected or scattered, means that the alpha particles, or the positive particles, must have been interacting with a positive nucleus, and thus we have the nucleus as the source of positive, and the negative electrons must be floating around in space in the outside. And the fact that so many passed through gave us an idea that there is a lot of empty space, because there is a lot of particles that do not interact with the atom when passed through a solid piece of gold foil. So the resulting atom contains three particles: protons, neutrons, and electrons. The electrons found outside the nucleus were the negative charges. The protons are found inside the nucleus, and the neutrons also found inside the nucleus. And they just add mass to the atom but have no charge. They virtually have the same mass as a proton, but they're just basically packing peanuts for the nucleus. Finally, the nucleus itself is small compared to the overall size of an atom. Extremely dense, and almost all the mass is right there in the nucleus. So these last few slides are lots of review, because this is not the first time you've heard about atoms and molecules. But matter is composed of either atoms or molecules. Atoms are small. Molecules are two or more atoms bonded together, acting as a single unit. They may be ionically bonded or covalently bonded. But a molecule is made up of multiple atoms. I rarely see people make this mistake, but it's worth noting that when you identify or write out molecules, we use a little subscript down behind to represent two of the same atom in a molecule. So this is an oxygen molecule, so we say O2. We don't say two O's, we say O2 because they're bonded together. The same with hydrogen, H2 rather than 2H. I identified this particle earlier when we were talking about the early atomic theory, but an isotope has the same number of protons, so two elements could be isotopes of one another, but they're isotopes because they're not the same mass. One has more neutrons or less neutrons than the other. So their properties are almost identical, but sometimes they're not. And if you add too many neutrons to a nucleus, it destabilizes the nucleus and then it becomes radioactive. And over time, the nucleus could break apart and result in new, smaller atoms. Most elements contain a mixture of isotopes. So if you grab a substance like out of the stockroom, like a pure carbon, or maybe even some pure copper. Maybe you've got a spool of copper wire at home. The copper itself is made of all the different isotopes of copper, roughly 46% to 54%. There's basically two stable isotopes of copper, and it's a mixture of both of them. Finally, the concept of the ion. It's an atom that has an imbalance in protons and electrons. And so an ion can either be positively charged if it has lost electrons. It's an atom that lost electrons and is now positively charged. Or an anion, which is negatively charged because it gained electrons. Well, that takes care of this video lesson. Thanks for watching.